Hello viewers, I Ch05 from welcome you to the episode on analysis of time series. In this script, we'll study the introduction of time series, model of time series and its components, problems of classification and methods of measuring trend. Before proceeding to study the various methods of analysis of time series such as the freehand, the semi-average, the moving average and the method of least squares, we'll first acquaint ourselves with the basic introduction on time series, its utility and few important definitions. A time series is a set of measurements on a variable taken over some period of time. The time frame of the recorded data may be an hour, a day, a week, a month, a year, or a fixed number of years depending upon the type of the event the data refer to. For example, hourly temperature of a particular city, or weekly earnings of workers in an industrial town, monthly prices of wheat. Most forecasting techniques involve the use of time series data. Time series analysis is of great significance not only to the economist and the businessman, but also to the scientists, astronomers, geologists, sociologists, research worker, etc. for the following reasons. First one, it helps in understanding past behavior. By observing the data over a period of time, one can easily understand what changes have taken place in the past. Such analysis will be extremely helpful in predicting the future behavior. Second, it helps in planning future operations. Statistical techniques have been evolved which enable time series to be analyzed in such a way that the influences which have determined the form of that series may be ascertained. If the regularity of occurrence of any feature over a sufficiently long period could be clearly established, then within limits, prediction of probable future variations would become possible. Third one, it helps in evaluating current accomplishments. The actual performance can be compared with the expected performance and the causes of variation analyzed. For example, if expected sales for the year 2010 were 10,000 refrigerators and the actual sales were only 9,000, one can investigate the causes for the shortfall in the achievement. Time series analysis will enable us to apply the scientific procedures of holding other things constant as we examine one variable at a time. Fourth one, it facilitates comparison. Different time series are often compared and important conclusions drawn therefrom. However, one should not be led to believe that by time series analysis one can foretell with 100% accuracy the course of the future events. After all, statisticians are not foretellers. This could be possible only if the influence of the various forces which affect these series such as climate, customs and traditions, growth and decline factors and the complex forces which produce business cycle would have been regular in their operation. However, the facts of life reveal that this type of regularity does not exist. But this then does not mean that the time series analysis is of no value. When such analysis is coupled with a careful examination of current business indicators, one can undoubtedly improve substantially upon guessed estimates, that is, estimates based upon pure guesswork, in forecasting future business conditions. In simple analysis, a time series is assumed to contain the following components. First one is secular trend. Trend is the long-term tendency of the time series to move in an upward or downward direction. It can be defined as a consistent long-term change in the average level of the forecast variable per unit of time. Consider the following figures showing the data on the color TV licenses issued over the period of time. So the data shows us a clear upward trend, we can see. Now let's see the next one, that is second one is seasonal variation. Seasonal variations are caused by the seasonal influence of spring, summer, autumn, winter or on business and the economic activities. Seasonality may also be referring to a season in context of a specific variable on which data is recorded. For example, in a touring business, season may mean the months of June, July and October, November, when number of touring people increase considerably. Thus, seasonality may refer to repetition of a pattern by months, by weeks or even by days of the weeks. Let's see the third one, which is cyclical variation. Cyclical variation, which are also generally termed as business cycle, are the periodic moments in the time series around the trend line. These are the upswings and the downswings in the time series that are observable over extended period of time. Neither the magnitude nor the frequency of the occurrence of these cycles are uniform. For example, a high boom in the stock market in India for a span of 4-5 years in 1990s caused by the Harshad Mehta factor can be considered as a cyclical component affecting the activity level of stock market over a period of time. The cyclical fluctuations are likely waves which come and go. At times, the cyclical waves prevails for a very long period of time, say 50 years, but these long waves are difficult to be distinguished as they get mixed up with the trend line. Now let's see the fourth one, that is irregular variation. This is taken to be random, non-systematic components affecting the time series through such unpredictable events as strikes, breakdowns of plans, non-seasonal illness, bad weather, etc. These variations either go very deep downward or too high upward to attain peaks abruptly. These do not occur frequently and are less important than the cyclical or seasonal moments. There are two models of decomposition of time series. First one is the additive model. This model is used where it is assumed that the four components are independent of one another. Independence is said to exist when the pattern of occurrences and the magnitude of moments in any particular component are not affected by other components. Under this assumption, the four components are arithmetically additive in the sense that the magnitudes of the time series are the sum of the separate influence of its four components. Thus, if it is taken to represent the magnitude of time series data at time period t, small t, then yt can be expressed as yt equals to tt plus ct plus st plus rt, where tt represents trend variation, ct represents cyclical variations, st represents seasonal variation, and rt represents random variation. Second one is the multiplicative model. This model is used where it is assumed that the forces giving rise to the four types of variations are interdependent, so that overall pattern of the variation in the time series is the combined result of the interaction of all the forces operating on the time series. According to this model, time series are the product of its four components, that is, yt is equal to tt into ct into st into rt. As regard the choice between the two models, it is generally the multiplicative model which is used more frequently. The reason being the most business and economic time series data are the results of interaction of a large number of forces which individually cannot be treated responsible for generating any particular type of variations. Since the forces responsible for one type of variation are also responsible for the other types of variations, it is the multiplicative model which is ideally suited for the purpose of decomposition of time series. Although it is a simple matter to classify the factors affecting time series into these four groups of analytical purposes, the actual application of the classification frequently presents serious problems. Seasonal variations are by no means always too uniform in amplitude and timing that their identification can be made with certainty. Consequently, the investigator is often hard to distinguish seasonal influences from cyclical or random factors. Long and severe cycles may, to some observers, appear to be changes in the direction of the regular trend. During the Great Depression of the 1930s, for example, many leading economists interpreted the existing condition not as a cyclic depression but as a secular stagnation. Another difficulty arises because the four components of the time series data are not mutually independent of one another. An exceedingly severe seasonal variation may aggravate or even participate a change in the cyclical movement. Conversely, a cyclical influence may seriously affect the seasonal. A very rapidly rising trend virtually eliminates the seasonal and the cyclical variations. Before beginning the actual work of analyzing a time series, it is necessary to make certain adjustments in the raw data. The adjustments are, the first one, calendar variations. A vast proportion of the important time series is available in a monthly form, and it is necessary to recognize that the month is a variable time unit. The actual length of the shortest month is about 10% less than that of the longest. And if we take into account holidays and weekends, the variation may be even greater. Thus, the production or sales for the month of February may be less, not because of any real drop in the activity, but because of the fact that February has fewer days. Thus, the purpose of adjusting the calendar variation is to eliminate certain spurious differences which are caused by peculiarities of a calendar. The adjustments of a calendar variation is made by dividing each monthly total by the number of days in the month, sometimes by the number of working days in the month, thus arriving at a daily average for each month. Comparable or adjusted monthly data may then be obtained by multiplying each of these values by 30.4167, the average number of days in a month. In a leap year, this factor is 30.5. Let's see the second one, that is population changes. Certain types of data call for adjustment for population changes. Changes in the size of population can easily distort comparison of income, production, and consumption figures. For example, national income may be increasing year after year, but per capita income may be declining because of greater pressure of population. Similarly, the production of a commodity may be going up, but the per capita consumption declining. In such cases where it is necessary to adjust data for population changes, a very simple procedure is followed. That is, the data are expressed on per capita basis by dividing the original figures by the appropriate population totals. The third one, that is price changes. An adjustment for price changes is necessary whenever we have a value series and are interested in quantity changes alone. Because of rising prices, the total sale proceeds may go up even when there is a fall in the number of units sold. For example, if in 2006, 1000 units of a commodity that is priced rupees 10 are sold, the total sale proceeds would be 1000 times 10 or rupees 10,000. Now suppose in 2007 the price of the commodity increases from rupees 10 to rupees 11. If the sale do not decline, the total sales proceeds will be 1000 times 11, which is equal to rupees 11,000. This increase in the sale proceeds, that is rupees 1000, is not due to an increase in the demand of the commodity, but purely because of the rise in the price from rupees 10 to rupees 11. Since value is equal to price per unit multiplied by the number of units sold, the effect of price changes can be eliminated by dividing each item in the value series by an appropriate price index. This, in fact, is the process of deflating, which has been discussed in the chapter on index numbers. Let's see the fourth one, that is comparability. For meaningful analysis of the time series, it is necessary to see that the data are strictly comparable throughout the time period under investigation. Quite often, it is difficult or even impossible to get strictly comparable data. For example, if we are observing a phenomena over the last 25 years, the comparability may be obscured by differences in definition, differences in geographical coverage, differences in the method adopted, change in the method of reporting, etc. For example, a sale figure for January 1990 may give the average for that month. Some years late, the corresponding sales figures may give the total for the month, or perhaps sales on the 15th or the last day of the month. If such types of changes are not taken into account, the data cannot strictly be compared and its analysis will lead to fallacious conclusions. The following methods are used for measuring trends. The first one is freehand curved method. First, we draw a curve after plotting the data of a given time series. It will be irregular as it would include short-run oscillations. We may observe the up and the down movement of the curve and smooth out the irregularities by drawing a freehand curve would eliminate the short-run oscillations and show the long period journal tendency of the data. This is exactly what is meant by trend. Let's see an example for this. The following are the figures of sale for the last 9 years. Now determine the trend line by freehand method. So plot it on a graph taking years on the x-axis and sales on y-axis. Second method, that is method of semi-averages. Under this method, the whole series is divided into two equal halves and the average for each half are calculated. If the data is for even number of years, it can easily be divided into two halves, but if it for odd number of years, we leave the middle year of the time series and the two halves constitute the periods on each side of the middle year. The average for a half is taken to be representative of the value corresponding to the midpoint of the time interval of that half. Feeders get 2 points. These 2 points are plotted on a graph and are joined by a straight line, which provides us the required trend line. We can also see an example for this as well. Let's fit a trend line to the following data by the method of semi-averages. So for the solution we have, since the data consists of 7 years, the middle year shall be left out and average of the first 3 years and the last 3 years shall be obtained. So the average of the first 3 years can be calculated as 102 plus 105 plus 114 divided by 3, or this is equal to 321 by 3, so this is equal to 107. And the average of the last 3 years is calculated as 108 plus 116 plus 112 divided by 3, which is giving us 336 by 3, so that is equal to 112. The actual data and the trend line are shown on the following graph. Let's see the next method, that is method of moving averages. A moving average is an average of fixed number of items in a series which moves through the series by dropping the top item of the previous averaged group and adding the next item below in each successive average. Thus, a moving average is computed by adding all the values of a certain number of successive periods and then dividing the sum thus obtained by the number of periods included. This average is considered as a trend value for the unit of time falling at the center of the period used in the calculation of the average. To compute 3-yearly moving average, for instance, the value of the first, second and the third years are added up, averaged, and the quotient is placed against the second year, then the values of the second, third and the fourth years are added up, averaged, and the average is placed against the third year, and so on. The moving averages series would yield a smooth curve provided the time interval chosen for computing the moving average is appropriate. Moving averages may be calculated for odd number of years like 3 years, moving average for 5 years, moving average for 7 years, moving average, and for even number of years like 4 years moving average, 6 years moving average, and so on. So let's see the next method, that is method of least square. The method of least squares may be used either to fit a linear trend or a non-linear trend. Under this method, a mathematical relationship is established between the time factor x and the variable y. A straight line of the trend is obtained by using the equation for the straight line, which is yt equals to a plus b, where the value of a is merely the y-intercept or the height of the line above origin. That is, when x equals to 0, y is equal to a, small a. The other constant b, small b, represents the slope of the trend line. When b is positive, the slope is upward, and when b is negative, the slope is downward. This line is termed as a line of best fit because it is so fitted that the total distance of deviation of the given data from the line is minimum. The total of deviation is calculated by squaring the difference in trend value and the actual value of a variable. Thus, the term least square is attached to this method. Note that the concept of the line of best fit is explained while discussing regression analysis. To estimate the value of the constant in the above equation, we start with normal equations. The following are the two normal equations for fitting a straight line by the method of least square. Equations are sigma y equals to na plus b times sigma x. This is equation 1. Next equation is sigma xy equals to a times sigma x plus b times sigma x square. This is equation number 2. So finally, we have reached towards the end of today's episode. So let's quickly summarize what we have learned today in the chapter of analysis of time series. In this chapter, we have introduced the meaning of time series analysis and the components of time series. We have also understood the utility of the time series and the various problems of classification in time series. We have also discussed the preliminary adjustments before analyzing time series and this method of measuring trend. So let us end today's episode. We shall get back to you with our next fresh episode on the topic binomial distribution. Have a great day. Thank you.